So let's take the fundamental theorem further and have it allow us factor a polynomial. So as we look at this polynomial here, x cubed plus 9x squared plus 23x plus 15, I have not told you how to factor a cubic that is not a perfect cube. But there is a strategy to use to where we can very easily factor this cubic polynomial. And that is by using the factor theorem. So note, if f of a equals 0, so a is the value I'm going to plug in here and it'll make this polynomial 0, then x minus a is a factor of that polynomial. So if you find a value that will make this polynomial 0, then that value can also be turned into a factor of this polynomial. And here's what it looks like. Step 1 is to find the zeros of this polynomial. What's the best way to find the zeros?
Looking at the exponents. Right? Wait.
Looking at the x.
Power. I don't know the word.
Somebody help her out. Looking at the x what?
The
x, right?
power. What?
The
power of x.
No, that tells me how many zeros I have. I have 3. But how do you find these zeros, like we talked about yesterday? There was the grandpa method, and what would you do for the modern method?
The constant over the.
What's that?
Set equals 0.
Okay, well, we'll assume it's set equal to 0.
So you put it in the graph.
You put it in a graph, right? You graphed it.
That's how.
And with the graph, I'm looking for the x intercepts. There we go. Don't know what y'all had for lunch today. Don't have it again, apparently.
Why?
Okay, so here is that graph. And you told me to look at the x-intercepts, like so. What are my zeros? -5, -3, and negative what?
-1.
So my zeros are -5, -3, and -1. That's step number 1. Step number 2 is now take each of these zeros and turn them into their factored form. And I'm going to show you how this works, and you're going to catch on pretty quickly. The factored form of x minus 5 is x plus 5. Because when I plug in this -5 here, that would make this -5 plus 5, which is 0. So you're basically, like it says here, given the opposite sign of your 0. So if I want to have the factor form of -3, it's going to be x plus 3. And if I want the factor form of -1, it's going to be x plus 1. Yep. You're taking your zeros, you're flipping their sign, and then slapping an x in front.
Nice.
And guess what? There is this polynomial factored. This polynomial factors into x plus 5, x plus 3, x plus 1. Bam, we're done. A very nice, convenient way of factoring without having to worry about all those different methods, like no fuss, the box method, AC method, whatever. Just find the zeros, turn them into factored forms.
So why did we learn the other one?
Because this only works if these are nice, even zeros. It gets a little bit tricky when these are irrational, or if these are like fractions. Looks a little bit different. But we're going to play nice for today. So when I look at this example here, I have x cubed minus x squared minus 14x plus 24. I want to factor this polynomial. So what was my first step? Graphing. Okay, so let me go to my graph here. There it is. Now what about this graph am I looking for? X-intercepts. I have one at -4, 0, 2, 0, and 3, 0, which means my zeros are -4, 2, and tres. So my zeros are -4, 2, and 3. Now that I have that, I can turn these into their factored form. What's the factored form of -4? X plus 4. The factored form of 2? X minus 2. And the factored form of 3. Look how quickly we factored that cubic. X plus 4 times x minus 2 times x minus 3.
Nice.
Essentially, when we talked about quadratics, we had the factor form, and we used the zero product property to turn these into zeros. In this chapter, we are going backwards. We have the zeros, and we turn those into factored form. So, real quick, while I take attendance, find my zeros, or sorry, That's step one, is to find the zeros, but then the ultimate goal is to factor this polynomial. Okay, tell me how many zeros does this polynomial have? So how many factors will this polynomial have? Very good. So let me graph it and look at my zeros. There we go. I should have 4 zeros, or 4 spots where it crosses the x-axis. There they all are. -5, -1, 0, and 3. So my zeros. -5, -1, 3, and 0. Now let's put this in factored form. What's the factored form of -5? X plus 5. What's the factored form of -1? X plus 1. Just a little ahead of myself. What's the factored form of 3? X minus 3. And what's the factored form of 0?
0.
X.
I don't know.
Well, let's look. Let's look at the theorem one more time. If f of a, so in this case the zero is 0, so f of 0 equals 0, then the polynomial is factor form x minus, in this case, 0. So let me look at, oops, wrong one. Yes, let me look at this. So the factor form would be x minus 0, which simplifies to what? Just plain old x. So the factor form of 0 is just x, which makes sense. Because last semester, when we had something like this and I asked you what's the 0 of this factor, what number would make x 0? Well, it would be 0. You would just plug in a 0. So there's my polynomial, all factored out. X times x plus 5 times x plus 1 times x minus 3.
No. Oh.
Okay. So now we looked at how to take our zeros and factor them. Let's look to see what happens if our zeros show up more than just one time. So I have this polynomial, x minus 1 squared times x plus 4 cubed. If I were to break this all down, it would be x minus 1 times x minus 1 times x plus 4 times x plus 4 plus times x plus 4. And if I were to take each of these factors and find the zeros of them, what would make x minus 1 0? Positive 1. So that would also be a positive 1. What would make x plus 4 0? A negative 4, which means that one's also negative 4, and that one's also negative 4. So I have 2 1s and 3 negative 4s. That is what's known as our multiplicities. It's how many times a 0 is counted as a 0. So note, if you look at it here, my 0 for x minus 1 is a plus 1, and that shows up 2 times. My 0 for this term, x plus 4, is minus 4, and it shows up 3 times. So you're basically solving the factor to find the 0, and then looking at the power to tell you how many times that 0 is in the polynomial. So this polynomial has 1, 2, 3, 4, 5 zeros. And if I look at the multiplicities, these should count up to 5 as well. 3 plus 2, 5. So, number 1. First, let's identify what our zeros are. So x minus 5, what's that 0? 5. X plus 2, what would make this 0?
Negative.
Negative 2. And x plus 5, what would make that 0? Negative 5. So now that I have my 3 zeros, I need to decide how many times do those zeros show up. So I'm going to call that my multiplicity. How many times does 5 show up? Twice. 2 times, right here. How many times does x plus 5 show up? Twice. How many times does negative 2 show up as a 0? What's my power? It is a 1 that you usually don't write, so its multiplicity is 1. So this polynomial has how many zeros?
I think you just think about something.
How many zeros does this multiplicity have total?
Single.
It has 5. You see just 3 original, but total it has 5. Cinco. Okay, so tell me. What is my 0 for number 2 here? This negative x squared. What would make that 0? A 0. And what would it be its multiplicity?
2 0.
Yeah, I have 2 zeros. Look at the power here. What about x minus 4? What would be that 0?
4.
4. And what would be its multiplicity?
1
Uno, yep. And then last but not least, x plus 2, what would be its 0? Negative 2, and its multiplicity. So how many total zeros does this problem have? It has 6. 3, 4, 5, 6. With 3 unique zeros. So that's basically how you identify multiplicities. How many times the 0 shows up. You look at the power above your factored form. It does get a little tricky though when we are trying to identify the graph. So notice, if you have an odd multiplicity, so an odd power, like 1, 3, 5, it will go through the x-axis. It will go through the point. If you have an even multiplicity, like 2, 4, 6, 8, 10, whatever, it will touch the point and essentially become a turning point in the polynomial. This is important because remember I said the whole point of this unit is to be able to sketch a polynomial by hand. So not only will you identify the zeros, but you will look to see what is the multiplicities of that 0. When you're trying to sketch this, an odd multiplicity will tell you to sketch it through that point, where an even will tell you that will become a turning point. So as we see here with this example, x, 0 is my 0. It has a multiplicity of what?
1.
1. So odd, so I'm expecting it to go through the point 0. And as I see here in the graph, does it not also go through? It does. If I look at x minus 1, what's my 0?
1.
1, with a multiplicity of 2, so that's even. So I'm expecting a turning point at 1. If I look at 1, I see it does have a turning point.
1, 2.
And what's my 0 here? X plus 1?
Negative 1.
Negative 1. With a multiplicity of 3, will it go through or become a turning point? It will go through. Odds go through. So looking at negative 1, I see it does go through. And then the last one, x minus 2 to the 4th power. It's 2, and it is a turning point. Now, you're not expected to graph this too much or identify, but you are expected to know odd multiplicities go through, even multiplicities create turning points. They touch the point. But note, if you were to sketch this by hand, as you can imagine some 40 years ago, they were probably very good at this, the higher the power gets, the flatter that point becomes. So if I were to raise this to maybe like a 5th power, this turning point will probably look more like this. In a, let's say, 13th power, it will probably look more like something like that, or of course that would be shifted more towards a negative 1. And notice how my square differs from my 4th power. Notice it's getting a little bit flatter here. And as this power increases, it's going to get more and more flatter. They had to know that back then, just so I can sketch it more accurately. But like I said, this is really what I want you to focus on or here. Now that doesn't mean I'm not about to expand your knowledge a little bit more. So number 1, I have, looks like 2 zeros here, negative 3 and 1. Negative 3 and 1. And with these, all of them come with multiplicities. Would you say the multiplicities at negative 3 is going to be even or odd?
Even.
Okay, even. So negative 3, I'm expecting an even multiplicities. This is what I'm expecting you to know, by the way. At 1, is that going to be an even or odd multiplicity?
Odd.
Odd, because it's doing what? Going through the point. We'll stop there for now. We'll look at number 2. I have 2 zeros here. -2 and 2, and all zeros have some kind of multiplicity, even if it's just 1, would you say -2 is an even or odd multiplicity?
Even.
Even, because it's a turning point, it touches. And what about -2, or sorry, +2? This is also even. So here's what's expected of you to know in this class. Now, to expand your knowledge a little bit more, let's see if we can actually figure out what these multiplicities are. Remember when I talked about turning points? Turning points equal what? Turning point equals n what? N1? What about N1? Plus 1? Minus 1, very good. Turning points equals n minus 1. Now, say you don't know what n is, but you can see it has how many turning points? 2. So I'm going to assume, remember this is just the most number of turning points, but I'm going to assume that the most number of turning points this polynomial can have is going to be 2. So I'm going to do 2 equals n plus 1 here. And if that's the case, what does n equal? 3. Subtract 1 of both. Sorry, this should be a minus 1. Let me rewrite that. Minus 1. So add 1 on both sides, add 1. I see n equals 3. Yep. So n equals 3 here. Now what does that number mean? It means I have what?
3 points.
Not 3 points, but 3,
Turning.
not turning points. N is your number of zeros, right? It's your highest power, the number of zeros you're going to have. So if I know I have only 3 zeros, and I have an even multiplicity here, like 2, 4, 6, 8, 10, and an odd number here, 1, 3, 5, how can I manipulate even numbers and odd numbers to get the number 3?
2 and 1.
Very, very good. 2 and 1. So at -3, I have a multiplicity of 2. And 1, I have a multiplicity of 1. Because I'm assuming that this is the maximum number of turning points I have. Therefore, that means n equals 3. Therefore, the only possibility here is with multiplicity 2 and 1. Bam. And then you can work backwards. You can actually, since these are my zeros, put these in factored form. This is going to be x, what? Plus 3 squared, very good. Because that multiplicity in this one, x minus 1 is the 1 power. And I guarantee you that if you were to put this in a graph, you would get this exact same graph. Bam. Just from looking at the graph and knowing the x-axis, or the x-intercepts. Let's try to do the same thing here. This is a little cut off, but let's assume that this connects here and this goes on to infinity. So it has how many turning points? 1,
4.
2,
Just kidding.
3. So turning points is 3, which means n equals 4. So if I'm expecting 4 zeros, and I know both of these are even multiplicities, then what is the only possible values that can go into both? 2 and 2. Very good. 2 and 2. Because they have to be an even number, and they have to total to 4. Which means I also can find the equation. So it's going to be what? X minus 2, what? Squared, and x plus 2 squared. Bam. And if you graph that, you would get this graph. Some critical thinking there. Expand on everything we know so far, put it together. Comes to find out, we should have enough knowledge to write an equation given just its graph. No matter the polynomial, regardless of what it is or what it looks like. But again, don't mind so much what I just did in orange. Again, I just want you to focus on knowing this. Odds go through the point, evens touch to become turning points.